The year is 1800. A curious little invention is being talked about. It's called a microscope. What it allows you to do is see tiny little life forms that are invisible to the naked eye. Soon comes a medical discovery that many of these life forms are actually causes of terrible human diseases. Imagine what happened to the society when they realized that an English mom in her teacup actually was drinking a Monster soup. Not very far from here. This is from London. Fast forward 200 years. We still have this Monster soup around, and it's taken hold in the developing countries around the tropical belt. Just for malaria itself, there are 1 million deaths a year and more than 1 billion people that need to be tested because they are at risk for different species of malarial infections. Now, it's actually very simple to put a face to many of these monsters. You take a stain, like acridine orange or a fluorescent stain or Giemsa, and a microscope, and you look at them. They all have faces. Why is that so? That Alex in Kenya, Fatima in Bangladesh, Navjot in Mumbai, and Julie and Mary in Uganda still wait months to be able to diagnose why they are sick. And that's primarily because of scalability of this diagnostics is completely out of reach. And remember that number, 1 billion. The problem lies with the microscope itself. Even though the pinnacle of modern science, research microscopes are not designed for field testing, neither were they first designed for diagnostics at all. They're heavy, bulky, really hard to maintain, and cost a lot of money. This picture is Mahatma Gandhi in the 40s using the exact same setup that we actually use today for diagnosing TB in his ashram in Sevagram in India. Two of my students, Jim and James, traveled around India and Thailand, starting to think about this problem a lot. We saw all kinds of donated equipment. We saw fungus growing on microscope lenses, and we saw people who had a functional microscope but just didn't know how to even turn it on. What grew out of that work and that trip was actually the idea of what we call foldscopes. So what is a foldscope? A foldscope is a completely functional microscope, a platform for fluorescence, bright field, polarization, projection, all kinds of advanced microscopy built purely by folding paper. So now you think, how is that possible? I'm going to show you some examples here, and we'll run through some of them. It starts with a single sheet of paper. What you see here is all the possible components to build a functional bright field and fluorescence microscope. So there are 3 stages. There is the optical stage, the illumination stage, and the mask holding stage. And there are micro-optics at the bottom that's actually embedded in the paper itself. What you do is you take it on, and just like you were playing like a toy, which it is, I tab it off, and I break it off. This paper has no instructions and no languages. There is a code, a color code embedded that tells you exactly how to fold that specific microscope. When it's done, it looks something like this. Has all the functionalities of a standard microscope, just like an XY stage, a place where a sample slide could go, for example, right here. We didn't want to change this because this is the standard that's been optimized for over the years, and many health workers are actually used to this. So this is what changes, but the standard stains all remain the same for many different diseases. You pop this in. There is an XY stage. And then there is a focusing stage, which is a flexure mechanism that's built in paper itself that allows us to move and focus the lenses by micron steps. So what's really interesting about this object, and my students hate when I do this, but I'm going to do this anyway, is these are rugged devices. I can turn it on and throw it on the floor and really try to stomp on it. And they last, even though they're designed from a very flexible material like paper. Another fun fact is this is what we actually send out there as a standard diagnostic tool. But here in this envelope, I have 30 different foldscopes of different configurations, all in a single folder. And I'm going to pick one randomly. This one, turns out, is actually designed specifically for malaria because it has the fluorescent filters built specifically for diagnosing malaria. So the idea of very specific diagnostic microscopes comes out of this. So up till now, you didn't actually see what I would see from one of these setups. So what I would like to do is, if we could dim the lights, please. It turns out foldscopes are also projection microscopes. I have these two microscopes that I'm going to go to the back of the wall, and just project. And this way, you would see exactly what I would see. What you're looking at, this is a cross-section of a compound eye. And when I'm going to zoom in closer, right there, I'm going through the z-axis. You actually see how the lenses are cut together in the cross-section pattern. Another example, one of my favorite insects, I love to hate this one, is a mosquito. And you're seeing the antenna of a Culex pipens right there. All from the simple setup that I actually described. So my wife has been field testing some of our microscopes by washing my clothes whenever I forget them in the dryer. So it turns out they're waterproof, and right here is just fluorescein water. And I don't know if you can actually see this. This also shows you how the projection scope works. You get to see the beam the way it's projected and bent. Can we get the lights back on again? So I'm quickly going to show you, since I'm running out of time, in terms of how much it costs for us to manufacture, the biggest idea was roll-to-roll manufacturing. So we built this out of 50 cents of parts and cost. And what this allows us to do is think about a new paradigm in microscopy, which we call use and throw microscopy. I'm going to give you a quick snapshot of some of the parts that go in. Here is a sheet of paper. This is when we were thinking about the idea. This is an A4 sheet of paper. These are the 3 stages that you actually see. And the optical components, if you look at the inset up on the right, we had to figure out a way to manufacture lenses in paper itself at really high throughputs. So it uses a process of self-assembly and surface tension to build achromatic lenses in the paper itself. So that's where the lenses go. There are some light sources. And essentially, in the end, all the parts line up because of origami, because of the fact that origami allows us sub-micron scale precision of optical alignment. So even though this looks like a simple toy, the aspects of engineering that go in something like this are fairly sophisticated. So here is another obvious thing that we would do, typically, if I was going to show that these microscopes are robust, is go to the 3rd floor and drop it from the floor itself. There it is, and it survives. So for us, the next step actually is really finishing our field trials. We're starting at the end of the summer. We are at a stage where we'll be making thousands of microscopes. That would be the first time where we would be doing field trials with the highest density of microscopes ever at a given took place. We've started collecting data for malaria, Chagas disease, and Giardia from patients itself. And I want to leave you with this picture. I had not anticipated this before, but a really interesting link between hands-on science education and global health. What are the tools that we're actually providing the kids who are going to fight this monster soup for tomorrow? I would love for them to be able to just print out a foldscope and carry them around in their pockets. Thank you.